Okay, let's start with the second module. As I said, second module is about physical layer. Okay, so the first topic under this module is about digital transmission. Okay, so the data will be in the form of digital. Okay, so the first topic under this digital transmission is digital to digital conversion. That means if the data that we are supposed to transmit over the physical the transmission channel, then the data will, if the data is in the form of digital, okay, and this data has to be transmitted over the transmission channel, and if it is in the form of digital signal, then what is the process for involved with respect to this, that we are going to study here. Okay, so as we discussed, digital data data or analog data, right? So here we will be concentrating on digital to digital conversion. That means converting digital data into digital signal when it is transmitted over the transmission channel. Okay, so the converting digital data into digital signals, three techniques are used. Okay, the first one is line coding, second one is block coding, and third one is scrambling. I'll repeat. This conversion method, that is converting digital data to digital signal, is done by following three techniques. One is line coding, second one is block coding, third one is scrambling. So out of these three, you got to study only one method, that is line coding. Okay, just a minute. Okay, the first method that we are going to discuss today is line coding. So as I said, line coding is one of the technique followed to convert digital data to digital signal. I'll repeat, line coding is one of the technique followed to convert the digital data to digital signal. So now let us see this diagram, then you will understand. Okay, now consider this is the sender and this is the receiver, where you need to send the data. And as you know, at the physical layer, the data will be in the form of bits, right? So since here we are considering the digital data with respect to this topic, right? So digital data, in the sense what it is a sequence of bits, that is 0 or 1, right? So when this data need to be transmitted over this transmission channel, and it has to be delivered to the destination. Okay, now this data has to be converted into digital signal. Okay, then here at the sender side, digital data are encoded into digital signal. As you can see, this is the way how we represent digital signal, right? So at the receiver, once it is converted to the digital signal, that is digital data is converted into digital signal, and it is transmitted over the communication channel, and this digital data are recreated by the decoder. Okay, so whatever the digital signal received at the receiver end, with the help of decoder, the signal will be converted into or recreated into digital data. Okay, this is the process that is followed for converting digital data to digital signal, and this process is called as line coding. Okay, this is simpler. Now once you know what is line coding, now the next thing we'll see what are the types, or you can see different methods that are followed under line coding to convert digital data to digital signals. Okay, so as I said, data can be in the form of text, right? We discussed in the first chapter. The data can be in the form of text, or it may be in the form of number, or audio, video, image, or data can be anything, right? And when these data are stored in the computer, in the memory, then how it will be stored? Obviously, it will be stored in the form of sequence of bits, right? So this sequence of bits, I mean, it has to be converted into a digital signal when you are supposed to transmit it over a transmission channel, right? So that is line coding is one such method followed, right? Under this line coding scheme, we have two types, that is unipolar and polar. Okay, so under line coding schemes, uh, we have unipolar and one more is there. Sorry, I missed that. There are, see, under line coding scheme, actually there are 5 methods, okay, out of which you got to study 3 methods, that is unipolar, polar and bipolar. Sorry, in listing here I missed bipolar here. It is the first one is unipolar, second type is bipolar, and third type is bipolar. Okay, now we'll see each one of it. Let's start with unipolar. Okay, again I said unipolar is one of the technique followed under line coding. That means it converts digital data to digital signal. Okay, do remember. And you can see in this representation where x takes time and y axis takes amplitude. Okay, so here as you can see, digital data in the sense it is zeros and ones, or you can say sequence of bits, right? And this data has to be converted into digital signal, and you know the digital signal is represented in this form. Okay, under unipolar scheme, okay, all the signals, okay, all the signals are on one side of the time axis. See, if you see this representation, you can see 0, 1 are presented at the at the one side of this time axis or amplitude. It is not represented the negative side, I mean other side of the time x axis, right? So that means that's why it is called as unipolar. Unipolar scheme says that all the signals, or you can say all the signal levels, okay, are on one side of the time axis. Okay, either it may be above or it may be below. If you represent signal at the below of this time axis, then will not represent it at the above of time axis. So if you look at this diagram, you can understand it much better, right? So I will repeat, unipolar scheme is one of the technique followed under line coding, which converts digital data to digital signal. Okay, under the scheme, all the signal levels. See, we started the levels of signal in the last module, right? This is one level and this is another level, right? So all the levels of the signal are on one side of the time axis. Okay, that is about unipolar scheme. Okay, so uh, you can see here, this is also called as non-written zero. You remember, unipolar scheme is designed as a non-written zero scheme in which positive volt defines bit 1 and 0 volt defines bit 0. Okay, here 1 represent positive voltage and 0 represent 0 voltage. Okay, and it is called as non-written zero scheme as well. Okay, this is about unipolar scheme. Okay, so next, as I said, the second type under line coding scheme, right? That is polar scheme. Under this scheme, we have 3 types. One is NRZ, that is non-written zero type. RZ represents zero, written zero, and third one is biphase. Okay, biphase. The first, let's start with the first one. We'll see each one of it, what exactly it is. Okay, the first, or before starting with NRZ, here with respect to polar scheme, the voltages are on both sides of the time axis. See, if you consider this example, here voltage levels or the signal levels are represented only at one side of the time axis, right? If you consider the next method here, it is represented on both sides of the time axis. That means it can be positive or it can be negative, right? So here, if you consider here, if you all the signals are above this time axis, right? So that means all these signals are positive, right? So if I represent any signal below this time axis, that means it represents negative signal, right? So that is what it says. Let's consider an example. The voltage level for 0. See, if you want to represent 0, then it can be positive and the voltage level 1 can be negative. See, in this diagram, I mean in this representation, 1 is positive, right? So if I represent below this time axis, this voltage can be negative, right? So that is what the scheme says. Okay, and in this polar non-written, the first type, let's consider the first type, that is non-written zero encoding, the first type under polar scheme. In this coding, we use two levels of voltage amplitude. So let's see that the two version of it, that is NRZL and NRZI. So I'll repeat. Under NRZ encoding, for the type, we follow two versions, that is NRZL and NRZI. Now we'll see what is NRZ. See, NRZ stands for non-written zero, right? And this NRZL represents NRZ level and NRZI represent NRZ invert. Okay, so these are the two versions under NRZ. Okay, let's see that here. As you can see in this representation, I've represented NRZL and NRZI. Okay, let's start with NRZL. As I said, NRZL says it is a non-written zero level. Here, the level of the voltage, okay, the level of the voltage determines the value of the bit. I'll repeat. Here NRZ level, the level of the voltage, okay, the level of the voltage determines the value of the bit. Okay, you can see here, let's start, the bit is 0. Okay, so it starts from here. When there is 1, there is change. Okay, when there is 0, then it goes straight. Okay, when there is 1, again it changes. Okay, this is non-return to 0. That means the signal can be positive or signal can be negative. Okay, I hope you understood this. It's a simple one. When you represent 0, it's the same. Okay, when there is next bit, that is 1, then there will be change in the transition. Okay, that is about NRZ level. Or I'll repeat it. The level of the voltage determines the value of the bit. So you can see when it changes its level, it specifies there is a change in bit. Okay, you can see here, if it is 0, there is no change, right? So that is about NRZ level. Next, we'll see the next type under NRZ, that is I. NRZ I. That means it is invert. Okay, here you can see the change or lack of change in the level of the voltage determines the value of the bit. Okay, I'll repeat. That means lack of change of the level. See, there no change, when there is no change in the level of the voltage determines the value of the bit. Let's see that. See, with respect to this example, the first bit is 0, right? So it starts from here. Okay, what is the next bit? Next bit is 1. So that means there is a change. Okay, the third bit here, it is 0, right? So that's why it is no change here, no change in the transition. Okay, again next bit is 0, so that is again no change. Okay, and the next bit is 1 here. So when it is 1, it has to change. Okay, so that is what it says. I hope you followed here. See here, when there is, see here, 0, 1, there is a change. When it is 0, again no change, right? So in the same way here, but it is inverted. It starts with 0. When there is 1, there is a change. Since next bit is 0, there is no change here. Okay, again it is 0, again it is no change. Then the next bit is 1, again it changes. Okay, so you can see here there are hollow circles here and filled circles here, right? So hollow circles represent no inversion. Okay, no invert. That means it's represent the next bit is 0. When there is a filled circle, then it says there is an inversion, that is invert. So it specifies next bit is 1. I hope you understood this. Do you have any doubts in this? Do you understand this? Yes? I'm audible, right?
Yes, ma'am, understood.
Okay, okay. So this is the simple one. You have to remember it. Okay. So next type is what? It is return to 0. That this is the second type under polar scheme. Okay. So here you can see return to 0. In short, it is represented as RZ. Actually, in the previous method, that is non-return to 0, there is a problem with this encoding. It says that in with respect to this, the sender and the receiver clocks are not synchronized. Okay, so what the rate at which the bit is generated at the sender side, that should match with the rate at which the bit will be received at the receiver side. Okay, to keep track this, the clock will be maintained at the sender side as well as receiver side, and these clocks should be in sync form. Okay, so whenever there is a what communication between sender and receiver, the clock should be in a synced form. Okay, so when non-return 0 method is used here, here the clocks are not synchronized. So that is the problem with this method. So if the clocks are not synchronized at the sender and the receiver side, what happens? The receiver will not come to know when one bit is ended and the next bit is started, because there is no synchronization. Okay, so to overcome that problem, next math scheme is or encoding scheme is used, that is return to 0. Okay, this scheme what it does, in this method it follows three values. One is 0. Okay, another one is positive, another one is negative. I will repeat. Return to 0 overcomes the problem that we faced in the non-return to 0 method, where clocks are not synchronized at the sender side and the receiver side. Okay. So with the help of return to 0, we can solve this problem, where return to 0 follows three values. One is 0, another one is positive, another one is negative. Okay, these are the three values followed here. Here you can see the signal changes not between the bits. See, in the previous method, you can see the signal changes after completion of one bit, right? After completing 0 bit, there is a change, right? So here in this method, it is not the case, because you can see here the signal changes not between bits but during the bit. Okay, so let's see this example. See here, the signal goes to 0 in the middle of each bit. Okay, so let's consider this example. Let's consider 0 bit is transmitted in this way, and let's consider it is a negative here. Okay, so it starts from here. So in the previous case, it used to be like this, right? One second. Huh. See, in the previous case, we used to represent like this, right? This complete this thing. The zero means it starts from here and it comes till here, right? Whereas in return to zero, at the middle of the bit, it changes transition, right? So it starts from here and it make a change in the middle of the bit and it returns to zero. This is zero, right? This is zero. This is positive side, right? This is negative side, right? So it starts from here and it returns to zero at the middle of the bit, and then it changes, right? So it says the signal zero goes to zero. The signal zero, this is signal zero, right? The signal zero goes to 0 in the middle of the bit, right? And it remains there only until the beginning of the next bit. Okay, so 0, right? It will be there in that level itself until there is a change in the bit. Okay, next bit is 1, right? That's why it changes here. It level changed. At the middle of the bit, it comes to 0 and it stays there until the next bit. Okay, I hope you understood this. I'll just summarize it again. Return to zero is this another type followed under polar scheme, and it solves the problem that we faced in a non-return to zero. Okay, so this return to zero follows three values. One is zero, another one is positive, another one is negative. Okay, so with respect to return to zero, the signal changes not between the bits. It doesn't changes. It will not change between the bits, but during the bit. What it is, that is the signal goes to zero. The signal goes to zero in the middle of the each bit, right? And it will stay there only until the beginning of next bit. Okay, so this is what this is all about return to zero. Now there is a change in each bit transmission, right? See, to transmit this bit, it need two signals. That because it has to change the, it has to come back to zero, right? Wherever it is, right? Either it is in the positive side or it is in the negative side. There is a change that the signal has to come to zero here, right? So this means to transfer one bit, we need two signals that is coming here, here, and here, right? So this requires two signals to change and to represent one bit. So therefore it occupies a greater amount of bandwidth, because I'll repeat, to transfer one bit, okay, it requires two two signals, right? So two signal changes is it required to transmit one bit. That's why it occupies greater amount of bandwidth. That is what given in this points. Okay, that is all about return to zero. Next, third method under polar is biphase. Under biphase, we have Manchester and differential Manchester. Okay, so I'll repeat. This is biphase is the third scheme followed under polar. Okay, under biphase, you got to study two types. One is Manchester and the second one is differential Manchester. Again, do remember all these methods are followed to convert digital data into digital signal over transmission channel. Okay, so first we will see what is Manchester. Okay, so if you look at this representation, it will easy to follow. Here you see the duration of a bit. Duration of a bit is what? This one bit duration is this much, right? The duration of the bit is divided into two halves here. See, this is the duration of bit, but it is divided into two halves. You can see this is one half and this is another half, right? So it is divided into two halves. The voltage remains at one level during the first half and moves to another level in the second half. See, at one half part, it remains at one level, right? And at another half, it will move to another level, right? See, this is first half, this is second half, right? So to represent the 0 bit, it stays at one level, right? And at one half, and it changes in another second half, right? It moves to another level. This is one level, this is another level, right? So in first half, it stays at one level, okay? And in next half, and the next half, it moves to another level, okay? So you can see 0 is divided into two halves, this part and this part can change, you can see here, okay? Next, it is 1, there is a change, and it is also divided into two halves, and it changes the level in each part, each half, right? And goes same with next bit. Okay, this is all about Manchester. Now the second type under this is differential Manchester. See, actually, this differential Manchester is the combination of return to 0, okay, and non-return to 0 I. So the differential Manchester is combination of this and this. Let's see this, okay. So as we studied, in return to 0, there is a transition in the middle of the bit, right? So let's see, see here, in return 0, there is a transition in middle of the bit. The combination of return to 0 and non-return to 0 I represents differential Manchester. Okay, let's see that. So in differential Manchester, uh, there is always a transition at the middle of the bit, right? As per the return to 0, there is a transition at the middle of the bit, right? This is middle of one bit, isn't it? But bit values are determined at the beginning of the bit. So it determines the value of bit. See here, it's same with invert as we discussed in the NRZI. Okay, so in differential Manchester, as per return to 0, it changes at the middle of the bit. It returns to the 0 at the middle of the bit, right? And with respect to I, if there is what if the next bit is 1, then there is no inversion. So I'll just start with, see, this is 0, right? This is 0, right? No inversion when there is 1, right? And when there is 0, there is inversion. So you can, one second, this pointer. Okay, see, this is middle of the bit, it returns here, right? 0. So next bit is what? It is 1. So there is no inversion. Okay. Next, if it is 0, that is next bit is 0, then there is inversion. Okay. So you can see here. When it is 1, there is no inversion. Right? So see, when there is 0, you can change the changes here. When it is 1, it doesn't change, right? So this hollow and filled circle represents that. That is about differential Manchester. Okay, that is all about biphase. And the last type under line coding scheme is bipolar scheme. Okay, so bipolar scheme is also called as multi-level binary. Okay, bipolar scheme is also called as multi-level binary. Here also 3 values are followed. One that is 0. Where is it? 0, positive and negative. Do remember. In bipolar scheme, it is also called as multi-level binary. Okay, it follows three value. One is zero, another one is positive, another one is negative. Okay, the voltage level for one data element is zero here. Please remember here it follows three values, right? So data, and for one data element, the voltage level will be zero. See here for 0, but it is 0. I mean it stays at 0, right? So while voltage level for other elements alternates between positive and the negative. So this is just to say it follows three values. So with respect to bipolar scheme, it follows three values. One is 0, one is positive, and the last one is negative. Okay. So under this bipolar scheme, there are two types, that is AMI, and the second type is pseudo ternary. Okay, so this AMI stands for alternate mark inversion. I'll repeat, AMI stands for alternate mark inversion. Okay, so according to this method, that is AMI, you can see in this a neutral zero voltage. See when it comes, one second, zero, right? See the voltage is zero here. The data bit here, it is 0, right? So this represents neutral zero voltage. So when there is 0, it represents the zero voltage. Okay, when there is 1, alternatively it changes. See, when it first time when there is bit 1, it changes, right? It is at the positive level, right? So next you come to another, when there is the next bit as 1, then it goes to negative level. Okay, so when there is 1 bit data, if the data element is 0, then it represents neutral zero voltage. Okay, when there is 1, when first time 1 bit is, sorry, when first one bit has to be transmitted, then it represents the positive level. Okay, when the second time one present in the data, then it represents the negative side. Okay, so as you can see, when 0, it is a zero voltage. When it is 1, it comes to positive, and again the next bit is 0, that means again it is what, neutral or the zero voltage. Again next bit is 0, that is zero voltage. Again next bit is 1, it alternates to the negative level. Okay, this is how it says. So next type under bipolar scheme is pseudo ternary. That is a variation of this AMI itself. Okay, in pseudo ternary, what happens? It is the other way. When there is 0, it starts with the positive side. When it is 1, it is the neutral zero voltage. Again, when the second time 0 bit is present as a data bit, then it moves to the negative side. Okay, so again next bit is 0, again it moves to the positive side. When again data bit is 1, again it goes to 0 voltage, and when again 0 bit is encoded, it is again alternate to negative side. Okay, this is about pseudo ternary. Okay, so that is what I have listed as points here. Okay, so that's all. Let me summarize what we discussed. I know it's but difficult to remember all the things I discussed here, but summarize, glance it over. I mean, after the class, end of the day, you just go through it, you will understand. Okay. So in this chapter, we started with digital to digital conversion. So the line coding is one such process which is used to convert digital data to digital signal. Okay. So that is with the help of encoder and the decoder. As you can see, digital data is converted into digital signal, right? So there are three methods followed under line coding scheme. One is unipolar, second one is polar, and the last one is bipolar. Okay, so in unipolar, you have the signals are represented at only one side of the axis. Okay, so and next method we discussed is non-return to zero, right? Where two types are there, NRZL and NRZI. So this is how you represent it, right? NRZI here it inverts, right? No inversion if 0 is there. There is inversion if bit is 1, right? So that is what we discussed. And return to 0, it is for each bit, it returns to 0. I mean, in the middle of the bit, the signal returns to 0, right? So that is what about return to 0. And next is biphase, where we discussed Manchester and differential Manchester, where you can see here there is no change, and here you can see there is a change when one bit is encountered or if it is present in the data. And the last method is bipolar, where it is also called as multi-level binary. And in this, two methods are followed, or encoding schemes are followed. One is AMI, that is alternate mark inversion, and then the next one is pseudo ternary, where 0 represents the neutral voltage and 1 represents the positive and alternatively negative. And pseudo ternary is uh, a version of another version of AMI, where 0 represents the positive side and alternately it represents negative side, and 1 bit represents the voltage level as 0. Okay, that is neutral voltage level. So this is all about digital to digital conversion. So if you have any doubts, let us discuss.